So the second of our Polymers as Review mini lectures is going to focus in on the kinds of chemistry we learned in chapters 20 and 21, that up-down-out mechanism that we grew to know and love. So that's the realm of condensation polymers. But just a quick recap, so far we've learned that polymers are really different from what we've learned about so far. They're really, really big, and their bulk properties really make a difference in terms of how they behave. The only mechanism we focused on thus far is the free radical chain growth mechanism, and that's a good review of the radical chemistry we learned in initiation, propagation, and termination. Bottom line is, once you've made as many polymer chains as you can, because all of the monomer has been chewed up, eaten up, then you can add some other thing to quench any free radicals, and there's your product. One thing that we didn't cover and is discussed in chapter 26 is the fact that these chain growth mechanisms don't have to be radical. There are anionic chain growth mechanisms and there are cationic chain growth mechanisms. It really all depends on the initiation. So that's a good review too if you want to go into it. We won't cover it in a mini lecture. We're going to turn now to these condensation polymers. They grow by a different kind of mechanism called step growth, and the example we're going to focus in on is polyethylene terephthalate, PET polymers. They're also known as polyesters, and you'll see why in just a second. But before we do that, I want to show you a little bit about polyethylene terephthalate bottles and introduce you to the artist Chris Jordan, who has a really cool series of artwork called Running the Numbers. And this piece is called Plastic Bottles 2007. Now this is 60 by 120 inches, and when you look at it up close and personal, what you'll see is that it's made up of polyethylene terephthalate plastic bottles. This piece depicts the 2 million plastic beverage bottles that is used in the United States every 15 minutes. So if that doesn't convince you to use a water bottle instead of buying a new bottle of water, I don't know what will. But back to our polymer chemistry. We didn't say it was all going to be roses. Anyhow, polyethylene terephthalate is this guy. So first, let's focus in on the fact that it is a polyester. But other than that, what is the monomer? What is the repeat unit? And how do you suppose this thing is made? Well, the neat thing about these condensation polymers is that there's more than one monomer. So you've got a lot of flexibility, haha, no pun intended, on how you create your polymer. In this particular example, our two monomers would be ethylene glycol, which is right there, and something that will react with it, like this terephthalic acid, or perhaps some other leaving group X, maybe another ester. So what's going on here? Well, we can certainly imagine that with a little catalysis, maybe a Lewis acid, maybe a protic acid, we'll just go ahead and use the acid form of terephthalic acid. We can esterify this guy. And nucleophile attacks electrophile. We get our tetrahedral intermediate. going to cheat, of course. There's our tetrahedral intermediate. We're going to do a little proton transfer here. And kick out that good leaving group to give our dimer. Okay, well, what can happen next? Keep in mind that there's one of these and crap loads of the two monomers. So, needless to say, this guy is going to grow on that end, this guy is going to grow on that end, and ultimately we're going to end up with our big long chains of polyethylene terephthalate. So the monomers for this molecule are here and here, but the repeat unit is the whole thing. So that guy keeps repeating n number of times, where n is, again, a huge number. Another condensation polymer that you, I'm sure, have encountered, even upstairs in the OChem lab, is something called Bakelite. This was a huge technological breakthrough in terms of being able to form a plastic polymer that was really, really robust and resistant to heat. This guy is so rigid it is machined. So Bakelite is particularly rigid for two reasons. Because of the presence of the aromatic rings and the intermolecular forces between layers and layers of this polymer, and because it can cross-link significantly. So again, with a little bit of catalysis, we can see, this is a great review of what? Electrophilic aromatic substitution. So we'll, again, just be pretty boring and just use a proton catalyst. What do we get? We get the carbocation intermediate. And so phenol reacts with formaldehyde to give this carbocation intermediate. Deprotonation to regenerate the aromatic ring takes us to our now substituted phenol. And as you can imagine, protonation again, and loss of a leaving group to make a very, very stable benzylic carbocation. Well, there you go. What's in the vat? More phenol. What can that phenol do? It can undergo electrophilic aromatic substitution, do a Friedel-Crafts with that carbocation intermediate, and so on and so forth, until you have strung together all those phenols with these one-carbon bridges that have come from your formaldehyde. Naturally, you can imagine, I hope, that there's the possibility to form one-carbon bridges at the para position all over the place, so that you get this really, really hard, rigid, very stable polymeric material called Bakelite. So we've already gone through that, the mechanisms, the electrophilic aromatic substitution. Another opportunity for review is stereochemistry. Okay, so polypropylene, doesn't matter how you make it. We could make it via a radical mechanism or anionic or cationic. Certainly anionic is a lot less likely because there's nothing electron withdrawing in this molecule to make an anionic intermediate more stable. But there it is, polypropylene. Well, what you should think about when you look at polypropylene is, each one of those is a stereocenter. Yikes, egads. Is there any way I can make this molecule so that all of those methyl groups come out pointing towards me? Well, yes, there is. And it's not something we can do in sophomore organic chemistry, but it is something we can do in the realm of organometallic chemistry. So you could either take the polymer course with Ted Papenfuss or my synthesis course to learn a little bit more about that. But basically, if we just throw in a proton, what we'll end up with is what's known as atactic polypropylene, which is just random stereochemistry, and it turns into a kind of a soft mess, if you will, not a rigid, structurally rigid, structurally stable polymer, whereas isotactic polypropylene is much more crystalline and stiff, if you will. So we'll end up this mini lecture with an example. Here is a representation of lycra where these ends just keep going, growing. What are the monomers? What are the repeat units? What does this molecule, how is it made? It's a condensation polymer. You can see that there are ester linkages. There are amide linkages. Excuse me. What do we have here? Well, focus in on what's repeating, and you'll see that this very stable aromatic diamine or dianiline is one of the monomers. Okay. Oh, looks like we got another one over here. Oops. Oh yeah. Looks like we've got ethylene glycol again. Okay. And what's this stuff in the middle? Looks like we've got a third piece here, right there. So we'll put an X group there. It looks like lycra is made up of 3 monomers. The green circled one here, the dianiline in the middle, which we're seeing again on this end, and ethylene glycol. And you're getting a picture of how many variables there can be in creating just the right polymer with just the right properties for the application. So that's it for mini lecture 2. The third one will wrap up with biomolecules, which will review all kinds of things from earlier on in the semester.